So today what I'm going to be presenting is a work, so like the title in the program is called Optimal Transport Distances or Markov Chains. There's a small change in this title because now we know how to do it from sample streams. And I hope that you're going to understand what this means at the end of this talk. So I have a couple of disclaimers to make. First is that I'm a bit of a tourist in optimal transport, so I don't know as much as most of the previous speakers in the room here. So this is really my first entry into this area. I hope that I'm not going to say anything that's terribly stupid about this. And the other disclaimer that I want to make is that time and space is going to be discrete in this talk. So I already apologize for that. This is a bit of a trigger warning, I guess, for many people. This is a big, big no. This is no serious math if there's no continuous time. Well, so I hope that you're going to be able to tolerate this as well. And all of this is based on joint work with my friends here at UPF, Sergio, Anders, Ludovic, and Javi. All right, so let's do this. Right, okay. So the type of question that we are trying to address in this line of work is the following. How do I compare stochastic processes? How do I quantify the intuition that if I look at these sample realizations of random walks of Markov chains on the real line, how do I quantify the fact that this one looks more similar to this one than it does to this other one? And these two things also look more similar to each other than they look to everything else on the other side. So how do I build a quantitative measure of similarity between stochastic processes and Markov chains, to be specific? In particular, how do I build an embedding of stochastic processes into a space like this, and how do I measure distances between them? So there are many reasons to study this problem. My reason is that I want to use this for representational learning and reinforcement learning. In short, this is about answering the following question. Imagine that I have some high-dimensional process, let's say like a stream of video, a stream of audio, radar, whatever sensor I have, and I want to compress them into a low-dimensional representation. And I want to compress them in a way that somehow this compressed process stays close enough to the original process, right? So that somehow the two objects do not drift away too far away from each other. And then the big question is, okay, how do I define close enough? What does it mean for a high-dimensional process to be close to a low-dimensional process? And I'm going to use the language of optimal transport to answer this type of question. I need to figure out the optimal way of using this remote thing. There's an angle. Okay, right. Okay, this is not the perfect version of the slides that I had in mind, but it's gonna be okay. So some of you may have seen some version of this talk where I start with defining the problem, walking through a few failed versions of a solution attempt, and then giving some algorithm that is going to give you a tractable solution for solving the problem for known Markov chains. Well, this is an updated version of that talk where we're going to have stochastic optimization methods that is going to be able to solve the problem based on samples only, and you're going to see what that means. Okay, so I suppose just about everybody in the room knows what a Markov chain is. Put up your hands if you do. Okay, perfect. Okay, so I guess I can go like really fast. The Markov chain is just a stochastic process, which is a joint distribution over infinite sequences that starts from an initial state x0, and then all the following states depend on each other in a Markovian way, right? So in order to predict the next state in a probabilistic sense, I don't need to remember the history of the process. I only need to remember the immediate previous state. There's this little animation thingy that is, I guess, kind of unnecessary. But since many of you are mathematicians, let me just motivate you a little bit with some applications as to like, why this is cool, why this is interesting. What are some applications of these ideas, or what are some examples where this modeling tool can be useful? So of course, the simplest one is just a random walk on the real line, right? And then some classical examples that have been studied since the 60s, 70s is number of requests in a queuing system. How do I serve a sequence of customers that are coming my way? How do I model the length of the queue? Or sequence of observations from a physical sensor, as I'm illustrating over here. This can be often modeled as a Markov chain. Sequence of screens in a video game. These are all classical applications in reinforcement learning. Or another curious one that I'm going to return to later is a sequence of memory states of a computer program. And I guess the main reason to be excited about Markov chains, at least for many people in machine learning, AI, and so on, and this is an NP complete problem, is that this is really the standard modeling tool in reinforcement learning. Okay, so this is the precise setting that we're going to consider. We're going to have two Markov chains that we are going to try to compare to each other. They are going to be living on potentially different state spaces. Again, they're going to have potentially different transition kernels, and they're going to have potentially different initial states x naught and y naught. The reason that I'm saying potentially different is that the version where x and y are the same, px and py are the same, but the initial states are different. This is already something that's interesting and has been studied in the literature a bit. But think of all of these as different spaces, different transition kernels, and so on. So since I want to use the methodology of optimal transport, I need to assume access to some kind of a ground cost function that allows me to compare individual states of the processes, right? Because if I have no way of comparing individual states, then how can I hope to compare infinite sequences of these objects? Which is what I'm hoping to. So some examples to keep in mind are, for example, if x and y are d-dimensional Euclidean space, then you can think of the Euclidean distance, square Euclidean distance between x and y. If, for example, I have some sort of a labeling function that acts on the states, then I can just compare the labels, and that is going to give me a cost function. This is, for example, useful if I'm considering the example of computer programs, right, where I consider the internal state of the computer programs is whatever is there in the memory, registers, and so on. And the labeling function is going to be like what the computer program writes on the screen for a given state, right? And of course, when I'm comparing computer programs, I don't want to compare them in terms of what they are doing on the state space, right? I want to compare them in terms of what they do on the screen, right? What their output is. So this is a meaningful choice in that scenario. Or in reinforcement learning, when there's also a reward function that is defined on the state space, then I can just simply compare the rewards. And that is going to give me a meaningful cost as well. So I'm going to give you some running examples, which are going to be helpful in defining some failed attempts at defining a good metric, and then I'm going to arrive at a good metric eventually. So the two processes that I'm going to be referring to several times is these two processes that are Markov chains on the set of integers 1 through 10. The first I call scramble. This is just an IID sequence of numbers in 1 through 10. And the other one is what I call sawtooth, which is just a deterministic sequence that just goes 1, 2, 3, 4, 5, 6, and so on, and then reboots to 1 every 10 steps. So obviously these two processes are different, right? And any good distance metric that I define over these stochastic processes should be able to differentiate them. And if I'm comparing one process with itself, then it should result in a zero. And the ground cost that that one can consider here is just this Hamming distance between the states. Okay, so the very first attempt that one can think of, and this is something that many people suggest to me the first time that I tell them about this problem, is, okay, so why don't you just consider the stationary distributions of the two processes? Right, so let's just define this new x of x, which is just the stationary distribution of the chain, which is just the limiting frequency that the process visits state x. And then I can just compare the processes in terms of their stationary distribution. For example, I can take an optimal transport distance between the stationary distribution. So is this a good idea? So why is this not a good idea? Yeah. Exactly. For example, like these examples that I've given to you, I mean, they have the exact same stationary distribution. Scramble and sawtooth both visit each state uniformly, right? But they are terribly different processes, right? So this is a very bad idea for comparing Markov chains. Now, second idea can be the following. And this is a little better, but still not going to be perfect. I can already tell you. So I can just take two independent realizations of the chains, and I can run them out to infinity, and I can compare the costs. I can sum up the costs from 0 to infinity with some weighting to make sure that I get a finite number. This gamma is a so-called discount factor that is somewhere between 0 and 1 that makes sure that this sum is finite. So now the problem with this is that if the processes are indeed random, and if I run out X and Y independently of each other, then they're going to, these sample realizations are immediately going to diverge from each other, right? They're going to go two different ways, and that is going to give me, again, a failure mode. Yeah, so this is the problem that one encounters, is that if you run these chains independently from each other, they're going to diverge from each other, and the individual costs that you're going to be seeing are going to be terribly big. So in particular, if I'm comparing scramble to scramble, then I'm going to get a non-zero number. This metric is going to tell me that these are different processes, which is nonsense. So now the problem can be solved by allowing the processes to share some randomness between each other, right? To couple the two processes together so that if they can move together, they should be moving together. And if they cannot, well, then it's bad luck. Then they are definitely different processes. So what this pi means here is a coupling between the processes that is a joint distribution over the two processes, such that if I look at the x marginal of the coupled process, that should be the same thing as the mx process. And if I look at the y marginal of the process, then I should be recovering the y process. So it's just some clever way of putting together these two random processes. So what I'm showing here is really just realizations of the same two random walks as I had before on this previous slide, except that these are the independent realizations, and what I'm showing here are the coupled realizations. See, the two are still not exactly the same. These are different Markov chains, but they are coupled together in a way that they move together as much as they can. So there's one fine detail that is specific to this problem, that you want to capture the structure of these processes in the coupling that you construct. So in particular, the coupling that you construct in this expectation needs to be a so-called causal coupling of the two chains, which means that the coupled process itself needs to be a Markov process. So that intuitively means that the coupling should not be such that it couples together information that is happening in the future with information that is happening in the past. So the joint process, the coupling of the two, the x's and y's, should be such that in the end they should still be Markovian. And this is a good definition, because this finally differentiates between the different processes, and it does not conflate, and it does not tell me that scramble and scramble are different processes. So we are not the first to study this problem. Turns out that this problem can be formulated as a problem of optimal control. That you can think of finding this optimal coupling as an optimal control, a Markov decision process type of problem. And it is called the causal optimal transport distance between the two processes. And since it is an optimal control problem in a Markov decision process, it can be solved by solving this system of equations that is known as the Bellman optimality equations that are associated with the optimal control problem. So the specifics are not super important, because this is not really what this talk is about. What I need you to notice here is this is a nonlinear fixed point equation, that here on the right-hand side you have an infimum, which itself is terribly difficult to compute. This infimum involves solving an optimal transport problem. And you need to not only compute the solution to this, but need to do this many, many times until you can find a fixed point of this system of equations. So, if I were a mathematician, then, this would be the end of the story. Like in a mathematical sense, this problem is solved, right? There's not much to do. The solution is completely characterized. I know how to extract an optimal coupling from this. That's it. But since I'm a computer scientist, I'm really unhappy with this. This is really not the end of the story for me, because solving this system of equations is really, really terribly expensive. So what I'm gonna do now is give you a computationally tractable algorithm that can compute this distance for us and do it based on only on sample realizations of the two Markov chains. So yeah. Before I give you the solution, let me just quickly mention some more applications besides representation learning. So there are like some more applications within mathematics and theoretical computer science for this. So if you think about this question that I mentioned about Markov chains corresponding to computer programs and their labeling function being defined as the output of those computer programs. So answering this question, this optimal coupling question, this optimal transport question, can help you solve problems of formal verification. So people have been studying this question since the 80s. I have two implementations of the same computer program. How do I verify that they are doing the same thing? Turns out that the answer is can be found in terms of finding this optimal transport distance between those processes. It's called bisimulation metrics in the context of computer science. And of course, if you have distances between Markov chains, then it can be used for defining distances between other structured objects like graphs, manifolds, and so on. The couplings that you compute can be used for estimating mixing times and so on. All right, okay. So we started to work on this problem with my friends, some of whom are here. We had a NeurIPS paper in 2024 where we had a lot of fun. We managed to characterize a set of optimal solutions. We discovered the link between bisimulation metrics and optimal transport. This concept from theoretical computer science was connected with this concept of optimal transport from pure mathematics, which is totally new. And in case I know the kernels Px and Py, we managed to construct a computationally efficient algorithm that computes optimal transport distances for the first time in the literature with provable rates, convergence guarantees, computational complexity analysis, and so on. So we were pretty happy with this. But of course, it has a big limitation. And that big limitation is that this approach needs access to the transition kernels Px and Py. And if you remember my applications, specifically representation learning for reinforcement learning, I typically don't know what these transition kernels are. I only have sample realizations of the Markov chains, but I don't know what their transition kernels are. Of course, I can try to do like a plug-in estimator of trying to estimate the transition kernels first, and then using this algorithm to try to calculate the distance. But that really didn't work at all. We tried to analyze that, but to no avail. So we did something else instead, which I think is really cool and potentially scalable. And it's based on the following reformulation of the problem. So if you think again about the objective that I'm trying to optimize when computing my optimal transport distance, this infinite sum of discounted rewards under a coupling pi, that can be rewritten as this formula. This is really just a definition of the expectation, right? Just each cost weighted by the probability of seeing that state pair at time t. And then, since everything is finite, this is where it's useful. I can just simply swap the sums without saying any magical words like Fubini's theorem. And then I notice that, oh, okay, hold on. This object in the middle, maybe this is something of independent interest. This is the discounted number of times that the coupled process is going to be visiting state pair x and y, right? The total number of times that xt, yt is going to be x and y, discounted so that I get something finite. And these numbers, which I denote by mu pi of xy, are weighting cxy, right? So this reveals the kind of hidden linearity of the objective that I'm optimizing in terms of these variables, right? The objective that I have, which is terribly nonlinear in terms of pi, turns out to be linear in terms of this representation, mu pi. This is what I call the discounted occupancy of x and y under pi. Hidden linearity. This is going to help us design some really nice and satisfying algorithms. So the precise definition that we're going to be using in the derivation of the algorithm is this version of the occupancy measure, which I call occupancy coupling, which is the same thing as what you've seen before, except that this is over tuples of xy, x prime, y prime, which is the discounted number of times that I see xy followed by x prime, y prime. And turns out that the set of all possible such occupancy couplings are uniquely characterized by three properties: a coupling property, a causality property, and a so-called flow property. So let me walk you through each of these. So the coupling property, it says that okay, if I look at, so let me define these two objects first. So this new xx prime, this is the number of, the discounted number of times that the x process visits this state transition. And this new y prime is the discounted number of times that the y process visits this y prime object. So the coupling property of occupancy couplings is, of course, that if you marginalize out the y variables from the occupancy coupling, you should be recovering the new x. And if you marginalize out the x variables, you should be recovering the new y. That's kind of obvious, right? So basically, this whole mu should be a coupling of these marginal occupancies. Now, something that's more subtle is this causality property, which says the following: that under this occupancy mu pi, the following property should hold. If I condition on x, then the distribution of x prime and y should be written as a product distribution. So if I condition on x, then this distribution can be written as a product of the transition kernel multiplied by this distribution mu x, mu y given x, and the same holds for the opposite as well. So this is so-called causality property because it means that these distributions are independent of what y prime is. That I'm not allowed to use y prime as I'm coupling together x prime with y. And if I fold these two properties together, the coupling and the causality property, then if I put together the two equations, then I get this property that says that if I marginalize out y prime from this joint distribution, then what I should be getting is just the marginal occupancy of x prime multiplied by this conditional probability of y given x, some conditional distribution. So what I'm deciphering from this is that if I look at this marginal, then it should have this shape. It should be the product of the occupancy times some conditional distribution. And the final constraint is this something that I call a flow constraint, which somehow says that there should be some temporal consistency to this occupancy mu, which is most easy to understand if I just set gamma as 1, because then it essentially corresponds to a traditional flow constraint, or what physicists call a detailed balance constraint. And it essentially says that whatever mass flows into a state pair x and y should be the same mass as what flows out of the state pair x and y. I guess like this is the mass that flows out of xy, and this is the mass that flows into xy. So since these criteria that I listed, so it's kind of obvious that all occupancies satisfy these constraints, but turns out that the other direction is true, that if a function mu satisfies all of these equalities, then it must be an occupancy coupling. So if it satisfies the flow constraints and this coupling and causality constraints, then it's a valid occupancy. So why is this useful for us? So this is useful because, I guess the missing logical step here is that, remember that what I want to minimize is mu times c. Right. So my optimal transport problem can be written as this minimization problem. This is a minimization of a linear objective function, minimum of mu times c, subject to a set of linear constraints, subject to a set of linear constraints that are shown here. So this is a linear optimization problem, a linear program, which can be solved in a variety of different ways, like classic LP solvers and so on. But my favorite way of solving it is by primal dual methods. So essentially introduce Lagrange multipliers for all of these constraints, for the flow and coupling and causality constraints, write down the resulting Lagrangian function, which is just the original objective function, plus the Lagrange multipliers multiplying the constraint violations. And if I reorder this, I arrive at this function, which is some horrible function of mu, my other primal variable lambda, which appears over there. and the dual variables alpha, beta, and v, where alpha corresponds to this first coupling constraint, beta corresponds to the second coupling constraint, and v corresponds to the flow constraint. So, you know, if you just look at this, this just looks like a horrible clutter of math. But what's nice about it, and why we were very happy to eventually find this, is that this Lagrangian, if you inspect it close enough, it turns out that, that it can be written as an expectation of the sum of three terms. The first is an expectation under mu for some function of alpha, beta, and v of these samples that are drawn from mu. Plus you have an expectation with respect to nu x, the stationary distribution of the x chain, and an expectation with respect to nu y. And this is cool because now this means that this can be optimized by stochastic optimization. This can be optimized by stochastic gradient descent in particular, right? Because my objective function here, in terms of the dual variables, alpha, beta, and v, of course, they're written as expectations, which means that I can get unbiased samples of the gradients just by sampling from these expectations. And this is the very neat thing about this formulation that allows us to use SGD, or a standard algorithm, for solving the linear problem. So in particular, this is the algorithm. I know that this looks like a bit of a horrible mess again, so I'm going to simplify it for you and say that for the primal variables, we're going to be doing some incremental updates that are called mirror descent. And for the dual variables, we are essentially going to be stochastic gradient descent, thanks to the fact that we have the Lagrangian as an expectation. And importantly, this SGD steps only requires sample access to nu x and nu y. It never requires access to the transition kernels. I never need to have random access to the transition kernel. I only have samples from nu x and nu y. And somehow the logic here is that I'm trying to find the saddle point, the min-max of this Lagrangian, which is equivalent to the solution of the problem, by doing incremental updates to mu and incremental updates to alpha, beta, and v. And hopefully these two players are going to converge to a saddle point of this problem, which is what I'm after. Right. So we did a bunch of theory about this. We have this very nice sample complexity and runtime guarantee about this method. It says that the algorithm that I've just shown you, it is going to return an epsilon optimal estimate of the optimal transport distance that I'm after. After this many iterations, it's 1 over epsilon squared. It scales somehow with this thing that's called the effective horizon of the problem. And it has this scaling with the number of state and action spaces, which is, of course, what we are getting because we are considering unstructured problems without like any sort of like smoothness over the state space. So I was actually pretty surprised that we could get this dependence, because I would have guessed that we're going to have a dependence that looks like xy squared. Yeah. 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 Yes. 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 Yeah. Right. Yeah. Right. So if you just think about the original occupancy measures over xy, right, and if you sorry, I guess right. Yeah. So, okay. So the additional thing that this has on top of that is the causality constraint, right? Because if I just look at the optimal transport distance between x, don't know that there's like a direction of time, that x comes before x prime, and same thing, y comes before y prime, then I would not be able to get like this causal optimal transport problem. I need to impose this causality constraint on top of that. Uh-huh. 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 Yeah. So you see that on top of detailed balance, you not only need that, you need more than that, right? So you need some additional constraints to hold as well. That is not enough. So under that you would be saying that that a Markov process is at zero distance with its time reversal always. Yeah. Uh-huh. Yeah. Right. Yeah. So this is not the thanks to these additional constraints here. Yeah. And that's very important, right? Because I'm doing all of this because I want to come up with a distance that captures this causality aspect, that captures the direction of time as well, which is not possible if I'm throwing away this causality constraint. Yes, very good. All right. Okay. So this is the sample complexity guarantee that we have, and it's also a bound on a number of iterations that we have. So what's cool about it, I think, is that there's no hidden constants here. There's some log factors hiding, maybe like a log x, log y on top of this, but there's no assumptions about smallest visitation probabilities under the two chains. If I would be happy with such a result that assumes that that both of the chains visit all of the states with probability bounded away from zero by some epsilon, and I would be happy to have 1 over epsilon in this bound, that would be very easy. This one does not have any such thing. So this is a worst case guarantee that always holds for any pair of chains. And I want to emphasize that this is really the absolute first result of this kind. Like nobody else has considered this problem successfully. There is only heuristics in the reinforcement learning community that have been trying to compute these optimal transport distances based on samples, but nobody had like a provably efficient algorithm or some seed of it that we have here. Okay, so let's see some pretty pictures because I guess you still have the brain capacity to have that. So I mentioned several times that I want to use this for purposes of representation learning. And we tested this method on some toy example that is like a simple representation learning task. Just imagine the following problem that I call block Markov chains. Imagine that I have mx, which is just a random walk on the integers 1 through 10. And then I have my, which is the same process with some random noise added on top, right? So there's some ut, which is uniformly distributed over the integers 1 through 5. And they are all going to like perturb xt, right? But you see that in order to predict yt, I don't need to predict what this ut is. I only need to know what xt was in the previous round, right? So I don't need to like learn this this bit in order to predict the behavior of the process. And you see that these two processes should be similar, right? And they should be classified as similar by my distance. And xt in particular can be decoded without any ambiguity from yt. So we did this little experiment of just generating a bunch of samples from different mx processes. And okay, sorry, I guess like we have generated a sequence y 0 to infinity with a parameter 1/2, right? Which is the bias of the random walk xt. These were our observations, and we were trying to fit a process of xt's to it based on samples in order to figure out what might have been the real theta that underlie these samples. And this is the result that we get after computing the bisimulation metric, or the optimal transport distance between these sample processes. As you see, this correctly points out that the theta that is at the lowest distance from the observations that we get is exactly at 1/2. It doesn't really recreate the ground truth because we are not running it like long enough to get there, but it nevertheless immediately qualitatively identifies the correct parameter theta. And one funny observation that we made is that actually these lambda parameters in the optimization problem that I showed, they seemed like some annoying thing, right? We got some additional parameters to optimize over. I need to do some more mirror descent steps than I need to. I need to parameterize more, I guess, like neural networks if I want to use this in practice. So they kind of look annoying and useless, but turns out that they have an interpretation that, thanks to this their interpretation through the lens of this causality constraint, I can think of them as encoder-decoder pairs. So in particular, if I consider the previous example where I had this block Markov chain, I had these x's and these kind of y's with a bunch of like useless information added on top. So we just trained this with a number of samples that goes from like 500 to 5,000 or something like that. And then we just visualize what these lambdas look like, right? And you see that as I add more and more samples, this structure emerges very nicely, right? That says that the conditional distribution of x given y, the conditional distribution of what x might have generated my y, it's a uniform distribution. And after enough samples, I can just figure this out without like inputting any of these structural assumptions into my model. So of course, like after a few number of steps, this structure doesn't emerge as clearly. But as I add more and more, then I can figure out these conditional distributions. And I can think of these as an encoder of what is the conditional distribution of y given x, and this is a decoder, what is the conditional distribution of x given y. So in my mind, you can think of this as like a training criterion for like a representation learning model, or like a world model, if you like, to use fancy words. Something that takes like causality and direction of time into account. Okay, so I think I'm pretty much out of time. So the big message or the big thing that we are happy about is that, well, so now we can solve this problem. Now we can compare stochastic processes based only on sample realizations. To my knowledge, no other method can do this. We are really the first to do this, and we are really excited about this and the potential applications that it has in representation learning in particular. But you can think of other applications as well. For example, like formal verification of machine learning systems, like the applications in computer science, formal verification of computer programs. For example, if I want to verify my hypothesis that transformers learn gradient descent in context, right? I can just make this comparison in terms of bisimulation metrics. I shouldn't be looking at the memory states of these processes, like, you know, what internal representation gradient descent has about the two parameters, or what are the transformer states that are being generated. What I should be caring about is their actual predictions. And if I measure distances in terms of this distance, that would be that would enable me to make much more robust conclusions. But of course, there are many open questions, and the biggest one at the moment is, of course, like how to scale this up, right? Because at the moment, like this algorithm that I've shown you, this only works for this tabular case of small discrete state spaces, because I need to maintain these Lagrange multipliers one by one in memory, and I need to maintain these mu's in my memory as well, and I need to update them one by one as well. We have a bunch of different ideas as to how to go across this barrier and how to parameterize these updates. Like what is really promising is that actually this algorithm is gradient descent, right? So it's not just like a plugin into Sinkhorn, but it's something that can be parameterized in principle. And there are many other questions that are relevant for representation learning. For example, one can notice this very nice property of this distance, that it is actually differentiable with respect to the transition kernel. Because it's a linear program, the dual variables are going to give you derivatives as well. So that's all I had to say, at least in this version of the slides. I apologize for the little shambolic delivery. I had many more random math bits for you. We can talk about that at lunch. Thank you for your attention.